Welcome to all students. In this lecture, we study about the examples on linear transformations. Let us take one example. Uh, Let L from R4 to R2 be a linear transformation, and it is defined as L operating on X, Y, Z and W column vector with 4 rows, and we get the resulting vector is a vector in R2, and it is defined as X plus Y, and the second row is Z plus W. Okay, so we have to show that we have to check whether L is linear whether L is 1 function. Is L 1 1 mapping or 1 linear transformation? Second, is L onto linear transformation? So there must be a question mark. And C, we find the kernel of linear transformation. Find kernel of linear transformation and image of linear transformation L. Okay, and also find and C, D is find the value of L operating on a vector 1, 2, operating on a vector 1, 2, 3, 3, 4. So we will find the value of L of this vector and also find L operating on vector 5 minus 5 minus 3, 3. Okay, so now D is very simple. We write the answer. Okay, so as D is very easy to solve, first of all we solve that number D. So we will find the value of L operating on the vector 1, 2, 1, 2, 3, 4, and it is equal to, by definition we know that it gives by definition of linear transformation L, it gives a vector in R2, column vector in R2 with first entry is nothing but addition of first two entries 1 plus 2, and the second row is nothing but the addition of 3 and 4. So this is a column vector and it is equal to, so first element is 3 and second element is 7. So this is the result for first. Now we will find the value of Now we will find the value of L operating on the vector 5 minus 5 minus 3 3, and it gives, by definition of linear transformation L, it is nothing but a column vector with two rows. First row is 5 plus minus 5, and the second element of this row means second row is minus 3 plus 3. So finally we get a column vector with 0 0 entries. Okay, so in this way we solved our D part. Now let us go to the part A. So in the part A we have to show that we show that L is 1 linear transformation, 1 1 or 1 to 1 linear transformation. Okay, so to show that L is 1 1, what we do, so as given that L is linear transformation from R4 to R2, we take any two points, we show that so let us take any two points in R4 which are not same and show that their images are also not same. Okay, so let x is equal to x1 y1 z1 w1 and vector y is equal to x2 y2 z2 z2 w2 belongs to R4 be any two vectors such that any two vectors such that x is not equal to y. Okay, we show that now we show their images are also not same, means L of x is not equal to L of y. Okay, so for that, as x is not equal to y, as we are taking x is not equal to y, this implies that the column vector x1 x2 x3 x1 y1 z1 w1, this column vector is equal to the column vector x2 y2 z2 w2. Okay, so this implies that the x1 is not equal to x2, then y1 is not equal to y2, then z1 is not equal to z2, and finally w1 is not equal to w2. So from these equations we can write this implies x1 plus y1, okay, is not equal to x2 plus y2, and z1 plus z2 sorry z1 plus w1 is not equal to z2 plus w2, and this will implies that the two matrices, first matrix is uh, x1 plus y1, z1 plus z1 plus w1. This matrix is not equal to this matrix x2 plus y2, and second row is z2 plus w2. So elements are not same, therefore matrices are not same. Therefore but this left hand side is nothing but the L of x1 y1 z1 w1 by definition of given linear transformation, and this is not equal to this right hand side is nothing but L operating on vector x2 y2 z2 w2. Okay, so this left hand side is nothing but L operating on vector x, and this is not equal to L operating on vector y. Thus we have shown that whenever x is not equal to y, this implies that L of x is not equal to L of y. So this shows that L of y. So this shows that L is 1-to-1 linear transformation. Okay, now similarly, now let us take the next part, B part. B part is, in the B part we will show that, L is onto function, or we check whether L is onto or it is not onto. Is L onto? Question mark. Okay, so how to check ontoness of the linear transformation L? So as we know that, as L is a linear transformation from R4 to R2, and it is a linear transformation. So how to check ontoness of this linear transformation? So we know the definition of onto function. If every element in a codomain has pre-image. Okay, so let us take Z is equal to AB, A comma B belongs to R2, be any element or any vector, and we show that there exists vector x belongs to R4 such that the value of x under x is equal to z. So if we are able to find out that x, then we can say that L is onto function. Okay, so we know that for a real number a, we can find two real numbers. Say x1 and y1 such that a is equal to x1 plus y1. Similarly, for real number b, we can find two real numbers say z1 and w1 such that b is equal to z1 plus w1. Okay, now consider okay, or we can say let or we can write consider this thing. Consider the vector AB, column vector AB, but that column vector is nothing but A is nothing but x1 plus y1 and B is nothing but z1 plus w1, as we have seen above. And it is nothing but it is by definition of a linear transformation, it is nothing but the image of vector x1 y1 z1 w1. Okay, so what we get is, let x is equal to the vector x1 y1 z1 w1. Okay, therefore we can write vector z is equal to L of x. So thus we are able to show that L is on to linear transformation. Okay, L is on to linear transformation. Now the next part is to show that C part, and in this C part we will find the image of L, and then we find the dimension of image set of L. Okay, in the C part, okay, in the C part, sorry, that is not the C part. Our C part is different, and okay, so our C part is, here we show that find the kernel of L. Here in this part we find kernel of linear transformation L and dimension of kernel of L. Okay, so we know that as L is a linear transformation from R4 to R2 is a linear transformation, then we know the definition of kernel of a linear transformation. Sorry, the definition is kernel of L is equal to it is the set of all those x in R4 such that the image of vector x under L is a zero vector in R2. And just let us solve this. Let x is equal to a vector x x is equal to a vector x, y, z, w, column vector in R4, and 0 is a 0 vector in R2, 0, 0, column vector in R2, and to find kernel of L, solve the equation L of x is equal to 0. Okay, so L of x is, so by definition of a linear transformation L of x is nothing but the vector x plus y, z plus w, and it is equal to, we get a 0 means 0 vector in R2. Just solve this system of equations, you will get the kernel of linear transformation L. Okay, now so from this equality of the matrices we get x plus y is equal to 0, and z plus w is equal to 0. Okay, so here now how to solve this system of linear equations, that is very important. Solving this system of linear equations is important now. So from the first equation I can write x is equal to minus y, and from the second equation I can write z is equal to minus w. Okay, so let x is equal to a and z is equal to, b. So from this we have y is equal to minus a and z is equal to, w is equal to minus b. Thus we have vector x is equal to x is equal to x, y, z, w, and it is equal to, so value of x is a, y is minus a, then z is b, and w is minus b. But this vector I can write like this, it is equal to a into vector 1 minus 1, 0, 0, plus b into vector 0, 0, 1 minus 1. So see here, so vector x is nothing but this, and here ab, they are real numbers. Okay, so a and b are real numbers, a comma b, they are real numbers. So kernel of L is the set of all those vectors which is generated by these two vectors, so now kernel of, and these two vectors are linearly independent. Okay, so kernel of L therefore kernel of L is equal to it is the set of all those vectors. It is the set of all the linear combinations here. So all vectors in the kernel of L, they can be put in the linear combination of these two vectors, 1 minus 1 0 0 a into plus b into 0 0 0 0 1 minus 1 1 minus 1, such that a comma b belongs to R. Okay, so therefore the set therefore the set B is equal to B with two vectors, 1 minus 1 0 0 and 0 0 1 minus 1. This set contains two vectors which are linearly independent, and this set generates kernel of L, okay, or spans kernel of L, and this set contains only two elements, okay, and therefore the number of elements in set B are 2, or we can say that cardinality of set B is equal to 2, and B is a basis. B is the basis of kernel of L. Therefore dimension of kernel of L is equal to dimension of kernel of L is 2. Okay, so we found a kernel of linear transformation L. This is the kernel and the dimension is 2. Okay, so now we go to the image of a linear transformation. Okay, now we find now we find image of linear transformation L, okay, as L is a linear transformation from R4 to R2, and it is a linear transformation. Therefore, and we know that image of linear transformation L, it is nothing but it is the set of all the images L of x such that x belongs to R4. Okay, x belongs to R4. One minute. X belongs to R4. Okay, so this is the image set, and we first find the image set of a linear transformation L, and then we find the dimension of image set of L. A image set of L is a subspace of codomain, means it is a subspace of R2. That's why we can find the dimension of that subspace. Okay, so image set of L. Now let us go to the here now. Okay, so let x is equal to x is equal to x is equal to column vector x, y, z, w, and therefore belongs to R4. Okay, and therefore L of x, and image set is always a subset of R2. Okay, so L of x is 1 minute. So I want to find out image of the vector x under L, and x is here. Okay, so L of x is equal to, it is nothing but the x plus y, z plus w. Okay, so I z plus w. Now but L of x is nothing but the addition of, see here, it is equal to, I can write this vector like this, it is addition of x z plus it is addition of y w. Okay, and again is equal to, see here, it is equal to, it is a vector in R2, it is equal to, it is again, see here, first vector I can write addition of x 0 and addition of 0 z plus second vector is y0 plus 0w, and finally we can write x into vector 1 0 plus z into vector 0 1 plus y into vector, okay, into vector 1 1 0. Okay, and plus again we have okay, it was not necessary. Okay, so now it is a 1 0 or w into bracket 0 1 0 1, or it is not necessary to do all these things. So go to the straight way now. See here what we do. Okay, not necessary to do all these things, just concentrate here. Okay, so it is equal to, so 1 minute. Okay, and it is equal to, so this vector I can write as a linear combination of these two vectors 0, okay, and plus another vector is z plus w 0 1. Okay, so L of x is generated by these two vectors 1 0 0 1. So B is a set of vectors 1 0 and 0 1, and this set is linearly in independent, okay, linearly independent, and generates and generates the elements in image set of L. Therefore, B forms a basis for image set of L. Okay, and therefore the dimension of image set of L is equal to the dimension is 2. Okay, so in this way we have written the dimension of image set of L is equal to 2. Okay, so now we stop here. Our lecture is over. We stop here, and this is the end of this lecture. Thank you. Okay.